Hello AP. 8.3 is covalent bonding, which is the majority of the molecules that we actually draw in AP are covalent bonding. You just saw the video for 8.2 for ionic bonding. As I said, the AP tests, it's very rare that I've seen ionic bonding as a drawing type of question. Usually questions are asked about ionic bonding for like properties, okay? So the majority of the rest of this chapter is going to be focusing on covalent, and chapter 9 also is going to be focusing on covalent, which means we need to be very good at drawing and answering questions for covalent bonds. The vast majority of chemical substances do not have characteristics of ionic materials, which means the majority of the chemicals we come into contact with every day, I would say probably over 90% of the stuff we interact with, we eat, we wear, we drink, all covalent bonding, okay? Very rare do we actually come into contact with ionic materials. Most of the substances with which we come into daily contact, such as water, tend to be gases, liquids, or solids at very low melting points. Many, such as gasoline, vaporize readily, okay, which means it doesn't take a lot of heat to make gasoline evaporate. And it has a certain name too. It's called volatile. You're going to see this name pop up in chapter 11 when we start talking about properties of liquids. Many are in a solid form, as in like plastic bags, paraffin. If you don't know what paraffin is, it's a type of wax. Like if anyone gets their nails done and they dip their hand in wax, it's called paraffin wax. So basically that wax kind of, if you put it on your hands, it removes all the dead skin and cells that are pretty much left on your hands, and it makes it all nice and smooth. For the very large class of substances that do not behave like ionic substances, we need a different model for bonding between the atoms, which means when we draw them, we need to look at a different set of rules. So a scientist named Lewis, okay, which you've heard his name back in 8.1, Lewis reasoned that atoms might require a noble gas electron configuration by sharing electrons. Okay, remember with ionic is about loss and gain of electrons. Someone's got to lose it, somebody's got to gain it, even though they'll have a noble gas configuration in the end. However, with covalent bonding, we're talking about sharing electrons. In a chemical bond that's formed by sharing electrons is called covalent bonds. And remember, with covalent bonds, sometimes you may hear the word molecular bonding. Is because covalent bonds, they're molecules. Okay, so when we did math back in the day, Mr. Avogadro, when we would use 6.02 to the 23rd molecules, we were talking about molecular compounds, covalent bonding. Let's say we were looking at the most simplest type of bond, which is called diatomic hydrogen. Okay, so let's say right here we have two hydrogens, one hydrogen versus one hydrogen. And those are their very positive nucleus, okay, one proton in each one. And hydrogen also has one electron each. So if I wrote my dot structure for hydrogen, I have this hydrogen that has an electron, and I have this hydrogen over here that has his electron. So when two hydrogen atoms are close to each other, the two positively charged nuclei, aka nucleus, they repel each other. Now, why are they repelling each other? Because same charges repel. So when those two nuclei are trying to come together, they're repelling each other at the same time. And the two negative electrons, they're also repelling each other too. So these blue lines that you see right here, so aka the blue arrows. Okay, so the nucleus are repelling each other, the electrons are repelling each other. So how do you even get the two atoms to even come together to form a bond if you have both particles repelling each other? Okay, so the nuclei and the electrons are attracted to each other. So see these red arrows, the electron is attracted to this nucleus, and this electron attracted to that nucleus, and this one over here, and that one over there. So your red arrows, they are attractive because opposites attract. Okay? So because the molecule is considered stable, and remember, we're not going to use that word stable, we're going to say energetically favorable, okay, which means it's very low energy. We know that the attractive forces are greater than the repulsive forces. So those attractive forces actually make the attraction happen more than the repulsive forces. Okay, so even though the two nuclei and the two electrons, they're trying to get away from each other as much as possible, but those attractive forces are much stronger than the repulsive, and that's what makes those two atoms come together to form a bond. So the atoms in H2 are held together principally because of the two positive nuclei are attracted to the concentration of the negative charge between them, as you see in this figure. So in essence, the shared pair of electrons in any covalent bond, it acts like a glue that binds those atoms together. So if this is Mr. Hydrogen and his nucleus, and here comes his valence electron, and here's this Mr. Hydrogen and his valence electron, there's an attraction that happens, as you see in this very dense electron region. And when they come together, the nuclei and the nucleus, the nuclei and the electrons, they come together, and it's an attraction. So this electron gets shared with this electron, and what happens is you form electrons that are being shared between the two. Okay? And because it's H and H, it's the same element, it is shared equally. Now this is going to mean a lot when we get to 8.4, when how do we know if it's shared equally or not? And what does that mean if it's not shared equally? So right now, because both elements are the same, so same elements, okay, those two electrons, they're shared equally, okay? And when you have two electrons shared equally, you form what's called a bond, a covalent bond. And why is it called covalent? Because it's a nonmetal bonded to another nonmetal. So we're not talking about ionic for a while. It's all about the nonmetal side right now. Okay? So in this, when we have Lewis structures, the formation of a covalent bond, they're represented by those Lewis symbols. The structure of the Lewis symbols, we show that the electron pair, okay, so let me draw it again. That's called right there, that's an electron paired. And they are shared with this hydrogen, and it's shared with this hydrogen. And then eventually we represent that shared paired with a bond. Okay? And that bond, more particularly, what that bond is called, a covalent bond. Okay? Because it's nonmetals only. And these are what's called bonding electrons. Okay, because you're going to learn a name called non-bonding in just a second. So bonding electrons are the electrons shared between the atoms. But what if you have something like maybe chlorine? What if I wanted to draw diatomic chlorine? Well, chlorine, you got to remember, chlorine atoms, they have 7 valence electrons. So what happens is when you have chlorine and you draw your dots, remember 1 on each side, and then you double up according to Mr. Hund. And let's say I want to bring another chlorine, same thing. So when you form a bond, when you're drawing the Lewis structures and you're going to put 2 atoms together, you want to leave this electron on the inside. Over here, you want to put that electron on the opposite side. So that way you see this attraction between the nucleus and the electrons coming together, and then eventually those chlorines will come together and make a bond. Well, the problem is chlorine had 7 valence electrons, and now they're sharing those electrons. So now if I asked you how many valence electrons does that chlorine have, and I know you're probably thinking the number 6, but remember, ladies and gentlemen, they are sharing those electrons, okay? Those are sharing those electrons. So what happens is, when you're counting the valence now, this chlorine over here, he has those 6 plus this one. So now he has 8 valence electrons. And this chlorine over here is also sharing those electrons, and he also has 8. The name of the game, ladies and gentlemen, is still an octet rule. But what about hydrogen? What can you say about hydrogen? Does hydrogen has his octave? Well, originally he had 1 valence electron for each one. But now he makes his bond, and now how many valence electrons does he have? Well, he's sharing these electrons, so now he's got 2. And this hydrogen is sharing those electrons also, because it's sharing it equally. If they're the same elements bonded to each other, then those electrons are being shared equally. So bonding electrons are the electrons between that are being shared. But what about these guys on the outside? So let me do that in a different color. Let's go blue. So these guys right out here, okay? Unshared electron pairs. So these are the electrons that are in pairs, but they're not being shared between another element. We call these non-bonding electrons. So if they are shared equally, we call them bonding. If it is unshared pairs, and we have a special name that we usually call them. We call them lone pairs. Okay, the loner electrons. The electrons that are just fine just being with themselves. And we call these non-bonding paired electrons. But more specifically, you're going to see this word more. We call these lone pair of electrons. Lone pairs. Okay, so all of these right here, all of those are all lone pairs. And just like on this chlorine, same thing. But this one right here, that's a bonding pair of electrons. Okay? So make sure you know there's a lot of new terms that you've never seen before. So non-bonding versus bonding. Okay? And I prefer for non-bonding, you do call them lone pairs, is just fine. Okay? So these two words, you can use interchangeably. They mean the same thing. Okay, so let's do an example. Let's say you're going to show me how to draw silicone tetrachloride. Now remember, with this name, you're talking about non-metals bonded with non-metals. So now we name those prefixes for any of those that actually have a more than one type of atom. So we got tetra and chloride. Okay, so a little side note on the naming. Okay, so molecular compounds, aka covalent compounds, same thing. You name the nonmetal plus the nonmetal, but that second name, you change the ending to IDE. Okay, so silicone tetrachloride. And if you have any prefixes, you have to add them. Okay, just beware of the one. When to use mono and when not to use mono. Okay, so beware if it only has one. Okay, and if you don't remember, then go look at your chapter 2 notes, because it's in your notes. If I wanted you to draw the dots for silicone and for chlorine, okay, so first we need our periodic table. And if we notice on periodic table, the valence electrons for silicone sitting right under carbon, so he's got 4 valence electrons. Okay, so we're going to draw our 4 dots. Now chlorine, we just said chlorine has 7. Okay, now I want you to draw the molecule. All right, so if this is what silicone looks like, and each chlorine has 7 valence electrons, then what's the molecule going to look like? Okay, so rule number 1. The element, so this is the compound. Okay, so rule number 1. The first element is, I'm going to say the word usually, what's called the central atom. Okay? And I'm saying the word usually because you know sometimes we have molecules that start with hydrogen. So there are some rules coming in about 8.4, 8.5 that are very detailed rules. Right now we're just doing some basic structures. So silicone tetrachloride, the first element called silicone, he's usually going to be in the central atom. So we're going to put him right there in the middle. And we're going to put his 4 valence electrons. Okay, now I'm going to do this in a different color so you can see this. Now, the outside, number 2, we add what's called the terminal atoms. Now, terminal just means the outside atoms. So basically not the center atom. So I'm going to put a chlorine over here. And remember, every chlorine has 7 valence electrons. Okay? Now, I'm going to leave that empty space right there because I don't have 8. I'm going to leave that empty dot where I have 7. I'm going to leave it empty on the inside. Same thing over here for chlorine. I'm going to put one up here. And same thing. I'm going to leave that empty spot for an electron closest to silicone. And we're just going to keep doing that 4 times. Okay? Okay, so this is what's called the Lewis dot structure. Okay, so that's the dot structure. You're going to be able to do this eventually very fast where you don't even have to do what I'm showing you right now. You're going to go straight to the drawing. So then what happens is now they're going to start to form bonds. So the name of the game is an electron for each element. They have to come together to form a bond. So I need 1 electron from chlorine, 1 electron from silicone. And they're going to come together and they're going to form a bond, a covalent bond, because it's nonmetals and nonmetals. Even though silicone, I believe, is considered a metalloid, he still reacts like a nonmetal. And over here, they're going to come together and form a bond. So 1 of each and 1 of each. Like I said, eventually you're going to be very beast at this. And you're going to be able to do this in like seconds, okay? So what's called the actual structure look like with bonds? So I'm going to have my silicone in the middle. And I just formed 4 bonds, 4 bonding pairs of electrons. And each one of these chlorines, I'll do them in the red, they each have lone pairs all around them. So you're going to see questions about, as you see coming up, how many bonding pairs is in this structure. Okay? And I know my word's right there. Let me kind of erase that word atoms. So you can see those 2 electrons. Okay? Word to the wise. When you are doing your dots, your structures, ladies and gentlemen, you need to make sure that your dots are big and dark, okay? Because when you do something like that, and it's like I'm trying to grade it, or AP is trying to grade it, it's like, well, is that like a smudge? Or is that supposed to be there or not supposed to be there? So you want to make sure that the dot is round and dark. So now the question is, here we go. How many valence electrons surround silicone? So how many valence electrons surround him? So remember, every single one of these pairs of electrons, and I want to make some notes on here, these are bonding pairs of electrons, okay? Just like we said up there. And these guys in red, whoa, didn't mean that line to go like that. Where's my undo button? There you go. And these guys in red, these are non-bonding, aka lone pairs of electrons. Okay? So, question number 1. If you focus on silicone, how many electrons do you see right now surrounding silicone? Well, he's sharing these with chlorine, and he's sharing those, and sharing those, and sharing those. They're all sharing them. So if I focus on silicone, I see 2, 4, I'm sorry, 2. I don't want to put 4. Every bond has 2 electrons. So if I write that down, there's 2 being shared there, there's 2 being shared there, and 2 being shared there. So if I count that up, there are 8 valence electrons now surrounding silicone. And he now meets his octet rule. He's happy. And what about each chlorine? Well, look at the chlorines. So the chlorine right here, he definitely still has a 6. But remember, each chlorine is sharing those electrons with the silicone. So I have 2, 4, 6, but then I'm sharing also those electrons with silicone. So each chlorine also has 8. And how many bonding pairs of electrons are in this molecule? Well, every bonding pair is a bond. So I have a bonding pair right here. I have a pair right there, a pair right there, and a pair right there. How many bonding pairs? I have 4 bonding pairs. If I asked how many bonding electrons, then that would be 8. So be very careful that you understand what they're asking for. Are they asking for bonding pairs? Remember, pairs come in 2. Or are they asking about bonding electrons? Okay, so how many bonding pairs? There's 4 pairs. But how many electrons are surrounding that silicone? It's 8. So when nonmetals bond, they're trying to achieve that octet because that means every orbital is filled. Let's try another one. Draw the Lewis dot structure for nitrogen and fluorine. So nitrogen versus fluorine. Predict the formula of the stable binary, which means binary means only two elements in that compound. Okay, now you can have whatever subscript you want, but you can only have 2 elements if it's a binary compound. Are formed when nitrogen reacts with fluorine. Draw the structure. Okay, so first we need to figure out how many valence do they have? Before they start bonding, how many valence do they have? Okay, this one I actually told you the formula. I didn't tell you the formula here, so we're going to have to predict the formula. Okay, well nitrogen, if you look at the periodic table, he's in group 5A. So he's got 5 valence electrons. Okay, now Mr. Fluorine is in group 7A, so he's got 7 valence electrons. So fluorine's got 7 dots. Okay, so the question is, when they come together, do I need more fluorines, or is 1 fluorine enough? Well, look right here. I have an available spot to bond. I have an available spot to bond right there. And I have an available spot to bond right there. I can't do any bonding right there because they're already paired up. Okay, so I have these 3 locations that I can add this fluorine. So I know nitrogen, okay, he's going to be first because I asked you between nitrogen and fluorine. I put him first for a reason, so that way he will be your central atom. Okay, which means these guys are your terminal. But the question is, do I need more fluorine? And yes, I do, because I can only form that 1 attraction right there. So how many more fluorines do I need to fill this octet for nitrogen? Well, I'm going to need 2 more fluorine. So I'm going to need a fluorine over here. Okay, and then this nitrogen up here, this valence electron that is not paired up, well, I'm going to need a fluorine up there too. So I'm going to create a bond right there, and I'll create a bond right there. So then what does my structure look like? So I have my nitrogen and the central atom, and I formed 1 bond here, 1 bond on top, 1 bond on the side, but I still have those lone pairs sitting right there on the nitrogen. And then I have my fluorine surrounding it, but fluorine's got a lot of lone pairs. Okay, so I have 3 fluorines for every 1 nitrogen. So the formula that I created for this binary compound is NF3. And if you were asked to name that, you know you're going to be asked to name it, then you call it nitrogen. 3 fluorines is tri, and fluoride. And you know fluorine is definitely misspelled quite a bit. Let's make sure we don't put flouride. We have fluoride. And now you have your molecule. So how many bonding pairs of electrons do I have? Well, I have 3 of them. I have 1, 2, 3. Okay. And how many, what we like to call valence electrons surrounding the nitrogen? Well, remember, it's sharing. So if I look right here, he's sharing those fluorine, and he's sharing with those with fluorine, and he has those lone pairs. So every bond has 2 electrons. So 2, 4, 6, but then I have to count these guys. 7, and there's 8. So nitrogen has his 8 valence electron, and every single fluorine, they're sharing 2. So that fluorine has 2, 4, 6, and he's sharing with nitrogen 7 and 8. So every fluorine also has 8. Okay, that's the name of the game, ladies and gentlemen, is get to that octet configuration. Okay, so hopefully this is making sense to you. Like I said, we're just doing simple stuff first, and you know it's going to get complex eventually. So let's do one more example. Compare the Lewis symbol for neon with the Lewis structure for methane. In what important ways are the electron arrangements about neon and carbon alike? In what ways are they different? Okay, well, neon, noble gas, okay, and it's just the element. But then I have methane, and remember those names back from chapter 2, those alkane names, aka chapter 2. And just so you know, ladies and gentlemen, these numbers in the back of the problems, these are examples that I've taken from the book, so that way you can also see them there too. So page 308. And let's say you had to draw methane, CH4. Well, what is different about this? Well, this is a molecule. So I want to compare neon, that's an element, with CH4, that's a molecule. Okay? So first, what are the structures? So neon, noble gas, 8 valence electrons. Okay, so he is completely filled up. All of his valence electrons are all paired. Okay, but he's bonding just with himself. Okay, that's it. He's just a lonely electron, or lonely element. But if I have carbon, so versus CH4, how do I draw this? Carbon being the first element, he's going to be our central atom. Now if you notice on the periodic table, how many valence electrons does carbon have? And he has 4. Okay, so he's got 4 available spots to bond. And how many hydrogens do I have coming in? Well, I got 4 hydrogens coming in. And every hydrogen has 1 valence electron. So that means I have these 4 available spots to put a hydrogen, and then I can create 4 bonds. Just like that. Okay? Carbon is what we like to call the universal element because anybody in that group can bond the most with elements. He actually can bond 4 times with either the same element or different elements. Not a lot of elements can do that. Sometimes majority can do 3 or 2 or just 1. But carbon has his own science called organic chemistry because he bonds the most. Out of any element on the periodic table, he bonds the most. So we got to study him in itself. So carbon will form 4 bonding pairs around him, and each hydrogen will share those electrons with carbon. So the carbon has 4 bonding pairs of electrons. And every hydrogen is sharing those electrons too. Now, do I put any lone pairs? No. No lone pairs because hydrogen only has 1 valence electrons. So you will not see any lone pair electrons ever, ever, ever on hydrogen. It makes no sense, ladies and gentlemen, and I'm even going to highlight that bad boy. No sense whatsoever to put lone pairs on hydrogen. So that is my structure for methane, and that is my structure for neon. So what do they have in common? Well, what do they have in common is, so number 1, they have in common neon has 8 valence electrons surrounding him, but carbon does too. They want you to compare neon and carbon. Carbon also has 8 valence electrons surrounding himself too. That's how they have in common. They both will have the same electron configuration. So both also, after they bond, have the same electron configuration. And they both have their octet completed. But how are they different? Big difference. Is neon bonded to anyone? Is he bonding to anyone? No. So these are called non-bonded pairs of electrons. And we call those lone pairs. But what are those electrons called surrounding the carbon? And as we just said, those are called bonding pairs. So what makes it different is that the electrons on neon are non-bonded pairs, but on carbon, they're bonded pairs. So I know I'm out of space. So for neon, he's got 4 non-bonded pairs of electrons, versus carbon has 4 bonding pairs of electrons. Even though they both have their octet rule, it's just how those octet are arranged, or how their valence electrons are arranged around that symbol. Are they being bonded to another element, or are they just bonded to that one element? Okay, so that's how it's similar versus different. I like this question because I've seen a question like this before in AP where they want you to relate different structures. The last part that's in this video, this has been hit pretty big lately. Unit 2.2 is something about bond order. Okay, so represent the relationship between potential energy, and we usually abbreviate potential energy. Okay, and you would have saw this in 8.2 video, and the distance between the atoms based on the factor of the influence to interaction strength. Okay, so how are they interacted with each other? Is it a strong interaction or is it a weak? So in a covalent bond, okay, we already know covalent is nonmetals bonded to nonmetals. The bond length is influenced by the size of the atom's core and the bond order. There is a huge thing that they're trying to tell you right here. So both by size, aka the atom's core, okay, as in the nucleus, and the bond order. So what a bond order is, you can have what's called triple, double, or single bonds. Bonds with a higher order have shorter and have large bond energies. Okay, and I'm going to show you what I mean by that. So you can have structures that share electrons, okay, which means they are sharing 2 electrons. You can have elements sharing more than 2. So this is what's called a double bond. So there are 4 electrons being shared, because remember, every bond has 2. And then you can have what's called triple bonds. and that is the most you can ever have, which is 6 electrons. Okay, so you got to remember, in a bond, that is 2 electrons being shared. Now we don't know if it's equaled or unequaled until we get to that topic. Okay, so in a covalent bond, that covalent bond right there is 2 electrons being shared. Well, I'm going to kind of manipulate my lines a little bit because it means something. Okay, so I'm going to make these different. Oops. I'm going to make them different sizes because of that last sentence that I need to show you right here. Okay, so the bond length, these lengths of these bonds right here, there are 3 different lengths, are determined by the atom's core, how big is the actual atom, and the bond order. Bonds with the highest order have shorter bonds. So this is what's called a triple bond. Okay, and that right there is a high order. Okay, and because it's a high ordered, those bonds are very short. They're shortest bonds that there are. But this last part is what's called larger bond energies. If I was to break those bonds, you need a lot of energy to break them. Okay, and that's what we call by bond energy. You need extremely a large amount of energy, a lot, to break those bonds. So a double bond, okay, has a little bit longer bonds than a triple, okay, and a single bond that's sharing only 2, these are long bonds, which means the distance between those 2 atoms is very large. Okay, it's great. So because the distance is so large between them, will it take a lot of energy to break that bond apart? And no, because they're not that attracted to each other. They're just being held with each other with a force, but they're not attracted to each other like a triple bond because they're very, very close to each other. So the distance is large between the atoms. And because the distance is large between the atoms, if I was going to break that bond, I don't need a lot of energy. It's probably not going to take much energy to break. But regardless, ladies and gentlemen, regardless, anytime you break bonds, you always need energy. Okay, it's just like taking an electron. You always need energy. Always need energy. Okay, so depending on how big the atom is and how many electrons that they're sharing will determine 1, how long or short the bond is, and 2, how much energy is in it that you need to break those bonds. So right here is the notes, okay, with your drawings. It is possible for more than 1 pair of electrons to be shared. Okay, so single are sharing 2, double sharing 4, triple sharing 6, and that is the most. Bond orders is the number of bonds shared between the 2 atoms, and only those 2 atoms. Okay, so definitely some good vocab here. If it's sharing 1 pair, okay, remember 1 pair is 2 electrons. Okay, it's called a single bond. And when you would have this, you would have a long bond. But if you're sharing 2 pairs of electron and a pair, that means that there's 4 electrons. Then you would get a double bond. And what happens is you would get something like this. Okay, and I'm not drawing the lone pairs on it, but there are lone pairs for those oxygen. Okay, sorry, those 2 dots up there. And a triple bond, which is 3 pairs, are sharing 6 electrons. So what happens is diatomic nitrogen has a very short bond. But if I'm going to break through all those electrons, I need a lot of energy. Okay? So single bonds have very long distance between them, and triple bonds are very short distance between each other. It's all about being between each other, how big or how small. Okay? So we call that bond length. Bond length is the measurement between one nucleus to the other nucleus. Now, it's usually measured in a unit called angstroms, and it's a capital A with a little halo above it. We don't do the math with it. We're not even doing anything with it besides just saying in this structure who has long bond lengths and who has short bond lengths. Okay, I'm just letting you know it's measured in a unit called angstroms. Generally, big trend here, big trend. Bond distance decreases as you move from single to double to triple. And we just saw that. Singles have long, triples have short. Okay? We already know that. As you share more electrons, the shorter the bond between the two atoms. Okay, sharing 6 electrons, short bond. Got it. Okay? So if you had an example question like this, okay? If I have a CO bond length in carbon monoxide, and if I said the bond length was 1.13 angstroms, okay, whereas the bond length in CO2, and if it's CO2, okay, you would have both oxygens on the other side. According to this, it says the bond length for these is 1.24. Without drawing a Lewis structure, which this is not the complete structure, okay, just a basic sketch. Do you think the CO contains a single, double, or triple? So this one right here, comparing it to here, do you think this bond is technically supposed to be a double or a triple? Well, yes, because this is a shorter distance compared to that CO2. Compared to CO2, what actually is a shorter distance will then equal a higher bond order. And what happens, ladies and gentlemen, the true structure for carbon monoxide, there's actually a triple bond in the carbon monoxide. And I'm going to show you how to do that. And CO2, what actually is the structure? They're double bonds. Okay? And you'll learn how to do that. So the point is, ladies and gentlemen, it's this right here. The shorter the distance between the atoms, the higher the bond order. Okay?